Hello, it's Scott Manley here, and today I am looking at Project Orion, specifically the Project Orion mod created by Nyrath, which is quite possibly the most Kerbal propulsion system ever envisaged. It was originally imagined apparently in 1946 by none other than Stanislav Ulam, who of course went on to help design the hydrogen bomb. And yeah, it's really awesome. It is nuclear bombs exploding underneath this pusher plate to push the vehicle vertically. Now, of course, there's a slight bug that caused my nuclear engines to fire, so I switched over, but I decided I wasn't going fast enough, so I fired a more powerful version. And that more powerful version immediately shot me up to ridiculous speeds, and the shock was just too much for that poor pusher plate to manage. Separated my spacecraft into two parts, which of course can only result in disaster, right? It is a long fall back, regardless. It did not get very far. But the thing about Orion designs, or nuclear pulse rocket is the correct name, is that they are one of the few designs of rockets which are within our technological grasp. You know, we basically understand every single part of them more or less. But they can provide high specific impulse and high thrust, which is very important. We have high specific impulse engines in the form of ion engines, right? But they're very low thrust, and we have, things like Saturn V engines, standard chemical rockets that provide a lot of thrust. But they have really lousy efficiency, and if you remember my light speed video, the amount of fuel that you would need to, get up to near light speed was more than the entire mass of the universe itself. So here I have a nuclear rocket, a nuclear pulse rocket built on top of this mod, which was created by Nyrath. It basically has a bunch of different fuel types. They come in these cylindrical packs. You can be lazy like me and just use the 3.5 kilonewton or meganewton packs. The larger ones provide a bigger bump, but I'm just going to set this thing up with a kill rotation on the autopilot. It actually is incredibly hard to turn. You'll see that I have a whole stack of RCS tanks there. And where we are going is we are going to try and go to Joule. Now you see where it is there? It's actually pretty well lined up with us. Now, it's actually behind us in the orbit. In fact, it's about 180 degrees away from where we would want Joule to be if we were going to perform a simple Hohmann transfer orbit. But this is a nuclear rocket with ridiculous amounts of delta V. It has several hundred kilometers per second of delta V. And I can literally just point my nose in the approximate direction of Joule and go, full thrust until I've got a pretty close encounter, and then trim once I'm there. No need to worry about, coming around, about phase angles or any of that stuff. Just point and click. And by click, I mean explode things, and away it goes at ridiculous speeds here. This thing that I think is using the 20 meganewton explosives. That's vastly more powerful than the regular 3.5 that they originally talked about. One of the nice things about about this is you can load it up with different yields or whatever. But it turns out that when you looked at these things, you pretty much need the same amount of fissionable material, but you can adjust the amount of fusion fuel to it, and basically build variable yield warheads so that you can adjust the amount of thrust you're getting just by essentially tweaking it. And it's actually really interesting that it doesn't matter pretty much how big you build this. The amount of uranium and plutonium or whatever you need is roughly the same for the smaller ones versus the larger ones, because the smaller ones use less efficient explosives. Right, the larger ones get more of their energy from fusion, therefore they don't need so much fissionable material. But there it is. Look at this. We're up at 3 kilometers per second already. We have basically achieved escape velocity, and you can see that we're going backwards along our orbit. Now, if we keep this up, we will fall into the sun. But that's okay, because we're going to keep going after that, and we're going to go even further off towards Joule. So yeah, anyway, as I said, it was originally conceived supposedly in secret in like 1946 or thereabouts. But later on, it was actually picked up by Freeman Dyson, who's, you know, one of those great celebrated physicists who, of course, he's also the guy behind the concept of the Dyson sphere. This is someone who does, you know, likes to think big, let's say. So the idea of propelling a rocket using nuclear explosions is probably right up his alley. So yeah, he basically worked on that for a couple of years, but then in 1963 the Nuclear Test Ban Treaty basically meant that it couldn't be developed, you know, into a conventional... It couldn't be developed at that point because of international treaties. And there was also the problem that, you know, the US in the 1950s couldn't see a reason why they would want to launch 8,000 tons of spacecraft into space, given that they hadn't even got around to, you know, launching Mercury, or even Vostok for that matter. Yeah, you can see here the plate is oscillating in and out. The idea is you're exploding nuclear bombs near that plate and it's absorbing the force. The design that they came up with actually used specially designed warheads that formed a shaped charge, more like a nuclear shaped charge, which is quite a concept. It is actually a core requirement for building hydrogen bombs, apparently. The understanding of how to shape the explosion from a fission warhead so that it actually triggers a fusion explosion. So presumably adjusting these things to, you know, preferentially fire along one axis isn't such a problem. The force would be absorbed by that plate, and then the force would actually itself be something like 100 Gs, but they would allow the plate to move and oscillate back and forth at a certain rate. The idea being the shock wave would be transmitted more carefully to the pilot, so they wouldn't be feeling the 15 plus Gs every pulse that this thing is showing. These poor Kerbals are apparently not going to be enjoying themselves. Yeah, look at this, we're now like 14 kilometers per second relative to planet Kerbin, and we are moving off. We still haven't got our dual trajectory yet. You can see, of course, in the nav ball where we're going to have to aim eventually. The idea is that this is actually slightly in front of its orbit, so eventually we will get a close encounter, then we'll just trim the orbit using the smaller nukes from that point. I mean, it's important to realize, right, that the smallest you can make this vehicle is basically dependent on how small a nuclear weapon you can build, and there is a certain minimal size at which a certain minimal amount of fissionable material you need to make a nuclear weapon that will explode, right? You know, and you're basically then from that point on you're adding, you know, fusion payload to make it more powerful. But you know, the smallest thing I think they came up with was like a 300-ton spacecraft that was using it would have about 500 bombs, and each of those would be about 200 kilograms each. But really, you know, their designs went all the way up to like flying cities that would be, you know, half a kilometer wide and mass 8,000 tons. You know, they went all the way up the scale. But you know, this model here that they're using is actually probably smaller even than the smallest ones that they could figure, right? So it's not totally to scale. I would like, you know, a more realistic one that's maybe, you know, 40 meters across is in the base plate, but we all know that Kerbal Space Program doesn't behave well with those large objects. Anyway, you can see we now have a close encounter that is getting closer as these things fire. At some point we'll cut the main engine. The throttle does in fact work on this, you know. So there we go. Look, we actually got an encounter, and I pretty much didn't have to do anything but hold this surface attitude. There we go. Now I've turned off the big bombs and we're switching to the smaller bombs because we need to figure out what we're doing here. This will take a whole bunch of work, a whole bunch of maneuvering, which is why it's going to run at 4 times normal speed. This thing turns incredibly slowly. It is a hugely massive vehicle that, well, it turns like a giant block of metal that's being pounded by nuclear weapons, right? Anyway, so the Orion spacecraft was originally envisaged as being something that could be used around the solar system, right? And they the original papers, they looked at missions all the way out to Saturn, but one of the, extensions of this is that if you build an appropriate spacecraft, you can probably get them up to, decent fractions of the speed of light, right? You could build a spacecraft that could get to a few percent of the speed of light, using, $367 billion was the estimate in 1968. Okay, so there's been inflation since then, but, it doesn't actually seem that far beyond ridiculous, does it? I mean, theoretically, the ultimate speed of these things, including, speed up and slow down time, is probably, 5 to 10% of the speed of light. If you're just going to speed up and you're not going to slow down, 10% is doable. Carl Sagan famously said that it would be an excellent, a far more noble use of the world's stockpiles of nuclear weapons, which largely have acted as nothing more than a deterrent while sitting around not doing very much. Anyway, we aren't going nearly as far. We're just going to the Joule system because it's the easiest target, really, for these. It has a very large sphere of influence. But anyway, after this preliminary work, the engineers basically coined the Project Orion, and this is no relation to the crew capsule Orion. This is, the nuclear propulsion system we're obviously talking about. Now, they actually went out and they started working on engineering designs. They came up with the whole pusher plate concept, which originally they thought it would just be like springy airbags, but what they realized was that if they missed a detonation, if there was a bomb that didn't go off, then the rebound could actually tear the plate off. So they designed a vastly more complicated, detuned piston system. The idea was that it would not have a resonant frequency which was the same as the bombs they were firing, because that in itself could be dangerous. They had to come up with a method for deploying the bombs, and in fact they supposedly talked to Coca-Cola about the internal architecture for how to move these kind of bombs, which were very much like large soda cans apparently. They wanted to figure out how to move these around the inside of a spaceship, so they thought, oh, that's just like a vending machine, let's talk to Coca-Cola about it. Ultimately, they came up with that their plan was to fire the bombs through a hole in the middle of the plate, and after every firing they would close up like a cone to protect it and deflect the blast. But most of the force would be absorbed by the pusher plate and then ultimately transferred up to the spacecraft itself. And look, this is me kind of going around into orbit. It is really not great for fine trim maneuvers. I'm going to just try and put it into an equatorial orbit, and this takes a lot of small trims here and there, but ultimately it's possible. The bombs themselves would not explode right at the plate. They would travel, a fair distance away from it before they exploded. You don't want to have it too close because otherwise too much of the plasma is too hot and it causes more, damage to your plate. Although all the designs, except the really biggest ones, worked with the idea of the plate being ablated over time. They did design one which had a plate that would not ablate and would be cooled passively. It was something like, 20 kilometers across, so not the most compact vehicle ever designed. And actually, they did build test models of this, right? They actually built a test design which used chemical explosive pellets. They would fire it and explode it. And there's supposedly one which flew for like 20 seconds and it went something like, 100 and something feet in the air. And it returned to the planet or returned to the ground. It didn't really leave the planet, but it returned to the ground on a parachute. And it supposedly is in a museum somewhere. I think it's in the Smithsonian, but I'm not sure about that. There is a video out there, but I'm not sure I have the rights to show you it, so I'm not going to include it here. I'm going to leave finding the video as an exercise to the reader. So anyway, now we are in orbit. It is time for us to perform this landing. The landing is more or less left as an exercise to the reader, right? Now, seriously, we've done all this before. Rather stupidly, I have only brought the fuel tanks for this. I haven't brought giant fuel tanks on this design. That was rather stupid. Val was just the first moon that I got an encounter with. And also, because it's a stage further out, or stage removed from the spacecraft, its RCS was burned up first, so it has no RCS left on it. I'm going to have to dock this thing without the need for RCS. It's not like I've never done that before. But yes, I mean, you know, this is an example of a mission. We have so much delta V in the parent spacecraft. All we have to land is the smaller spaceship. We can leave everything else in orbit, since this thing turns incredibly slowly, or since the parent spaceship turns incredibly slowly. There's not much point in trying to land on it. In fact, you will see that it is an incredibly dangerous idea to land where your main propulsion is nuclear weapons, because the weapons were designed to explode some distance past the pusher plate, but if you land on that pusher plate, then the ground is immediately below it and there's now no space to detonate. So you need extra long lander legs. And the lander legs can't sit out there normally because you have a nuclear explosion there which will chop your legs off. So best to leave this thing in space and have have other spacecraft land on the surface. There we go, a little excursion to the surface using those much-loved nuclear rockets. Now, of course, these nuclear rockets are less efficient than a nuclear pulse rocket, because these are basically a nuclear reactor with hydrogen being passed over it, and the hydrogen is being heated to provide thrust. But that means the nuclear core can't get too hot, otherwise it will melt. With a nuclear pulse propulsion system, the bombs basically heat themselves up into a plasma that's millions of degrees centigrade in about, a millisecond or less. And that blob of plasma expands, pushing against the rocket and pushing it forwards. Of course, I did try landing one of these things on the moon by hand. This was an earlier design, let's say. It is very hard to maneuver, as I pointed out. Look at all that RCS just firing, trying to keep myself somewhat under control here. We're going to try and land it on the lunar surface, and we're just killing velocity very carefully. Notice the thrust is way down on this thing. I think it might actually be using the 20 meganewton versions. I had one of these with the 400 meganewton, and those things would literally tear the spacecraft apart half the time if you fired them at ground level. Not so much because of the acceleration, more because of the wind resistance. So there we are, we're just going to try and bring this thing down as carefully as possible. And yes, we're completely blasting a hole in the moon here. Yep. Come on. Adjust yourself. Oh dear, this is not good. Of course, I mean, the animation on this, I'm not sure how it works, but it does appear that the center of mass moves because you can see the camera moving. I'm wondering just exactly how the physics of the plate is simulated. Also, the plate, I think, should move more in a sinusoid, shouldn't it? There, look! Oh. That was a perfect landing, but the thing just disintegrated. I call shenanigans. That is not cool. Well, look, here we go. Try to land this thing on its back at least so Jebediah can get out. That is not cool. Yep, and there goes the rest of the rocket rolling away there. Well, it is Jebediah. I'm sure he can come up with a way to get home. Now, it may surprise you to know that this wasn't the most Kerbal thing I did with this pack. No, the most Kerbal vehicle award goes to this nuclear pulse rocket powered aircraft. I didn't have the procedural wings mod installed. I did have the fire spitter wings, which is why we use the K-17 bomber wings and a whole bunch of them. You'll notice that the tail drags a little, and it makes it very hard to get into the air, but that probably wins all sorts of prizes for the scariest aircraft launch ever. I mean, when you account for the nuclear explosions and bits falling off the aircraft. So yeah, I lost some of my wings, but look, it's flying! It is a nuclear pulse rocket powered plane. Now, one of my problems with this is that it was terrible to maneuver. I could roll it pretty well, but it wouldn't want to pitch up and down regardless how I moved the wings. But then I realised that if I added this extra set of wings slightly higher up, then it would naturally want to curve towards these wings. So basically, I created an aircraft which always wanted to pitch up, and by rolling over I was able to adjust itself into somewhat level flight. So there you have it, the most Kerbal of aircraft using the most Kerbal of propulsion systems. It is an Orion nuclear pulse aircraft. It's only using the 3.5 meganewton yield devices. I'm not actually sure what that corresponds to, and I'm presuming when it says meganewton, that's meganewton seconds, because of course you have to multiply newtons by time to actually get the actual change in momentum. Regardless, yes, we're going to try and land it at this airfield. You see, I flipped this thing completely upside down so I can pitch downwards. It does actually fly. I mean, this is not time accelerated, this is more or less real time. So, of course, as we're flying through the air, we're demonstrating one of the concerns that came up, of course, with detonating lots of nuclear bombs in the atmosphere is that you're throwing nuclear fallout everywhere. But they are air blasts, so it's a slightly less of a problem, let's say. All the same, I wouldn't necessarily want to be underneath its flight path for long after it, let's say. Dyson, in his papers, he estimated that launching one of these would increase the risk of worldwide cancer sufficiently that one more person would die. I'm not sure I agree with that assessment, but then again, he is a very smart individual, and so I'm not going to knock him. It is a very hard thing to estimate. Here, I'm just turning this, and oh man, I'm just going to make it, I think. Look how close we come to that mountain there. And so now I'm going up too much, so I have to flip it upside down so I can come back down again. Yeah, they're cutting the power. We're gonna try and bring this thing down relatively quickly. So I've turned it on its side so we don't get any lift anymore. And turn it. Get down. Hey, look at that landing gear, huh? Okay. Hey, it still has some of its wings left. Thanks for watching. I'm Scott Manley. Fly safe.